Good afternoon, I'm Jim. I am NEO's Chief Scientist, and I'm going to talk to you in this keynote before you get your beer about some stuff that I find interesting. And because you're, a trapped audience now and there's beer coming, you kind of have to put up with it for kind of 40 minutes. So, trekking boldly into the future, going who knows where. So here's the deal, right? The boss gets to come up this morning, and he gets all the good stuff, right? He gets all of the announcements and the fanfare and the yay procedures, yay drivers, yay everything. Because he's kind of the captain of our open source enterprise. I think I might have preferred like a collective groan, actually, at that. That might have been, fair enough. That might have been more appropriate. But look, right, so I'm just like the science guy. I just get to tell you about the kind of nerdy, geeky, sciencey engineering things that are going on, and I have to confess that actually here, this is not my work, right? I'm actually representing these people who made Neo4j 3.0 happen, and to whom I personally owe an amazing debt. Yeah, you wait till 3.1. Personally, I'm amazing. They're a fantastic bunch of people. So, given that I'm just the science guy, and I'm not like, I'm the Spock analog, I'm definitely not the suave Kirk analog, I have a problem, right? Because my marketing team said to me, well, what are you going to talk about? I'm like, crikey, I'm on often macabre, right? And whatever I'm going to do is going to sound ridiculously dull. So I said, well, give us an exciting biography, abstract. I'm like, right, I'll give you an amazing abstract. And then they said, oh, no, you can't do that. It was struck from the record. So it turns out that what I can do is I can science. That's important, because now I can actually say that. Because now I've got science. So I can say scientifically, I'm going to science the shit out of this. Because it turns out this thing here is known as a B junction. That is to say, it is a X out of Y a construct in language, published, referenced, that's science, in case you're wondering, referenced by Hoxhamer and Napoli in 1985, so I can now legitimately say to my marketing team that I didn't swear on stage, but I simply scienced the shit out of it scientifically. So, that being said, here's what I want to talk about this afternoon. And it's kind of a smorgasbord of... That's a bad word to say when most of your colleagues are Swedish, right? Because they're all going to be like, it's not pronounced that way. It's actually pronounced, and I just don't have the ers and the ers for it. So there's a bunch of stuff that I want to talk about this afternoon. I think about the Neo4j philosophy, kind of what guides us when we're building Neo4j, and we're building this graph tech that you guys are using to build fantastic systems. And then I want to kind of think about how we use Neo4j, how we use graphs in both online and analytical cases. I want to look at some of the kind of fun things we can do there. And then I want to talk a bit about the kind of technology choices that drive us in Neo4j and that are driving the wider data market in a kind of world where the data market is kind of getting all kinds of fun and crazy. And then I'm going to let you into the future, have a little peek behind the curtain of what's going on in the Neo4j labs. But I can't help think. It just isn't. You know that thing where you like stood up in front of 700 people and just your presentation isn't quite going the way you thought? It's just, hang on, just let me. That'll be just a sec. Yeah, I'm running Vista. It's embarrassing, isn't it? Hang on. Let's see. Chips, crisps. And, there we go, reset properly. So what we're going to talk, now we're on home territory. You're terrible people for encouraging that kind of behavior, right? If I was a child, you wouldn't do it. So let's take a look at the Neo4j philosophy. And the Neo4j philosophy, I think, follows very much the UNIX philosophy, right? It's do one thing, do it brilliantly. I think Neo4j does graphs, and it does them really rather well. In fact, it's kind of like this. Science, marketing team, it's science, I tell you. While the thing on the right definitely has more features, it has more stuff going on, it's certainly clear to me that the thing on the left is greater in value and safety than the thing on the right. So, that's kind of our philosophy in Neo. Like, we do graphs really well because we think graphs are good. And actually, when you start scratching the surface of domains, all kinds of domains, that you might not immediately think of graphs, it might not be obvious that they're graphy, it turns out that an awful lot of domains are very, very graphy. So doing graphs well is actually very useful because it caters to a lot of domains. For example, here is my recent Amazon shopping, which is, it's a good job. It's not. I cut out the embarrassing stuff. But anyway, it's a snapshot of my recent Amazon shopping. You might think, well, that's shopping baskets, right? What's that got to do with graphs? Well, actually, that's a transaction history. That transaction history may well be connected out to a product catalog. That product catalog may be used to do all kinds of clever recommendations, which Amazon don't currently do because they still sell me the pair of shoes that I bought the other week again. Right? They can start to do so many smarter things. So it turns out that lists are graphs. It turns out that books are graphs. Me and Ian Robinson wrote a brilliant book. It's this book. It's called Graph Databases because we have an imaginative naming scheme. It turns out that books are graphs. Documents are graphs, right? Documents are trees, but then those trees, you have cross-references between them. So even something as kind of that you might think of as just, that's just a dumb filing cabinet. No, not at all. Documents are graphs, and we can treat them accordingly and get value from them. The biggest document management system on the planet? Ever heard of this thing called the web? Right? It's a graph. And for good reason. It's very, very useful. Transport is a graph. The timetabling of trains, the timetabling of buses, the things that many of us here in London use every day, the TfL journey planner, it's a graph. All these things that aren't necessarily, that might seem rather mundane in the human world, it turns out they're very conveniently represented as these kind of graphs. I used to live about here. It's, for those of you who live in London, it's kind of like South London. It's a bit stabby. There's always a theme. So CAD drawings are graphs, and supply chains are graphs. And when you start decomposing these things, it actually becomes quite humane to work with all these things as graphs in graph tech. Spreadsheets are graphs. So Felian Hermans has been wonderful in explaining how spreadsheets are graphs, because not only do you have neighboring cells, but you have functions that connect cells. And in fact, she uses graphs to debug your crappy spreadsheets as a service. Brilliant, brilliant idea. And of course, we know that looking for murky doings in the offshore world is also a graph. That was the good Keynote. What we know here in the UK is one other thing. That awesomeness is a graph. Yeah, there's a whole bunch of people like, who? This, Doctor Who is a graph. Doctor Who is a wonderful thing. So I stole this, again, from Ian Robinson of Graph Databases fame, because Ian says I look like this guy. It's rather unfair on this guy, actually, this Sontara. He's quite a handsome chap, really. But actually, you can take something as esoteric as Doctor Who, which has this whole crazy mythical universe of aliens and time travel and sonic screwdrivers and Daleks. They're not pepper pots. They're very, very scary. And it has this whole real world. Don't worry, I'm not Fruit Loop. It does have a real world. It is real. It's the actors, it's the script writers, it's the sets, it's the people who cater the breakfast and all that kind of stuff. And the wonderful thing about graphs is you can fold all of that stuff into one graph. You can have the entire universe, meta-universe, I guess, of Doctor Who in a graph, and at query time, you can choose how many of those dimensions you fold into it. Graphs are a really wonderful, convenient thing for capturing even crazy stuff. To wit, actually, I just remember, there are people in this room who I've trained in Neo4j using Doctor Who. They learned far more about Doctor Who than they did Neo4j. But actually, try doing time travel in another database. You will tear out your hair, and you will have this haircut, and it is not a good haircut. Do this sort of stuff in Neo4j, it becomes perfectly reasonable. So it turns out many of the things that we see around us, many of the domains that we're exploring, we already know this. God rest his soul. So setting out my store here, graphs are very, very, very widespread. So, given that most domains now, I believe, are very, very graphy in nature, what kind of insight can we get from our graphs? So, online versus analytic processing. Now, many of you are data professionals, and many of you have lived in this kind of world. Yeah? Recognize that? Whoops, there we go, thank you. Cubes. And that's been okay, right? It's sort of served us reasonably, this OLAP cube with multiple dimensions. You kind of pull the data out of your database, and remembering, obviously, to know everything you need to know up front, because there's no going back once you start. And you do some ETL job and warehousing and consultants and then something reports, right? That's great. I actually don't think it's great, right? I think, that the kind of technical forces at play there often force us to do this kind of analysis. But it's not the only choice, right? We've seen now how Neo4j is democratizing the kind of sophisticated data analysis that was, decades hence, the privy of large multi-PhD organizations, multi-thousand PhD organizations. So, OLAP cubes have served their time. There are better ways of analyzing data, and can you guess what it is? Of course, it's a graph. Oh, that was a Rolf Harris thing. Oh, that's bad, you can't do that. No, Rolf, no, Jimmy. Okay, we're cool. Cubes are like granddad's tech, right? Actually, I think, in my experience, that graphs are a far better, at least a far more humane and expressive way of doing analyses of data sets, because it is the relationships that yield so much value when you're analyzing graphs. You can fold, your graph contains all the dimensions of your data, and you can choose at analysis time, at query time, which of those dimensions you're going to fold in. So we also have the real-time advantage that, we don't need to have this massive, big, stinking infrastructure, one cube per query kind of stuff. We just have the graph. The same graph that we use to power our online systems is the graph that we use to perform deeper, bigger analytic jobs. And graph theory, like 277 years old graph theory, is simply the most amazing tool for doing both reactive and predictive analytics. Because analytics isn't just about aggregates. It isn't just about crunch the numbers, 42 pops out. Analytics is about actionable insight, preferably before the event happens that you need to action. So you need some kind of predictive, actionable insight. Now, even with the wonderful World of Panama papers, we have reactive actionable insight. But graph theory gives us the ability to cheaply do predictions. So, of course, at the end of a very long day, everyone wants a crash course in graph theory, right? Thank you, Tobias, thank you. You know what? Out of mate, 699 people in the audience left me hanging, and you were just right in there, and big love, bruv. Oh, now you do. Now oh, yeah, I want in. This is like sea lion reaction at this point. No, of course, everyone wants a crash course in graph theory, because graph theory is awesome. Now, the simplest thing that you can do in graph theory is called triadic closures. And it's called triadic closures because graph theoreticians are up their own arses. Actually, what they really mean is make triangles. Science marketing team, arse is probably Latin. So, graphs, particularly graphs involving humans, love the triangles. Now here, it's a triangle, and you can see that it describes a little social network. In fact, it describes a little social network from the South Park universe, and you've got Kyle and Stan and Kenny, and you can see that these guys are friends. And actually, that's quite a stable structure, right? You feel that that relates to you, because if you were Kyle and Stan and you were mates, it's quite likely that Stan and Kenny will be mates and that Kyle and Kenny will be mates. You'll sort of provide a transitive trust relationship between some friends. So if you had a situation where you were friends with Stan and you were friends with Kenny, it's quite likely that at some point Kenny and Stan will be friends because you're kind of vouching for them, right? Your friends are probably compatible with each other because they're compatible with you. Yeah? Obviously, this is a computer audience, so most of your friends are online or imaginary or robotic. But hey, isn't the future wonderful? Now, that's nice. That's a nice, stable triadic closure. Also, it's kind of pleasant because it's all friendly and good. There is another triadic closure where we've got a rather less pleasant kind of structure. We've got this structure now where we've got this rather horrible chap, Cartman, who's friends with Craig, but he's an enemy of Tweak, right? Cartman is a really objectionable young man. Now, this is a bit awkward, right? It's a bit awkward, because Cartman's friends with Craig, Craig's friends with Tweak, Cartman doesn't like Tweak. Now, I'm not saying this doesn't happen in human networks, because, basically, we're a bunch of douchebags sometimes. But this is kind of awkward, right? Because like, Cartman's all right, all like, hey, Craig, let's go and beat the shit out of Tweak. Science, awesome thing. And like, Craig's all like, no, I quite like Tweak. I don't know how Craig sounds. He doesn't sound British for sure, but Craig kind of likes Tweak. He's like, no, Cartman, Tweak's my friend. I don't really want to go and beat up on him. That's kind of sucky. So this is kind of weird, and the graph doesn't like this. This is unstable, right? The kind of graph refuses. And you know this, right? Because in your lives, you don't optimize for this, right? You don't optimize for hanging out where one person doesn't like another person in your little group, right? It's really awkward. It takes a lot of beer to get over that, which we'll come to soon. Then there's a third class. Now, this is, by the way, not at all nice, but it's stable. So you've got the class here where Cartman is friends with Craig, and both Craig and Cartman hate Tweak. So this means they can gang up on him, and like, kids are bad, right? Let's get this straight, right? When you were kids, you were bad like this. Kids are evil little creatures. But they can now gang up on Tweak. Now, this is bad from a human point of view. You're a bad species. However, from a graph theoretical point of view, from a triadic closure point of view, these are stable. There's nothing trying to change. This is a low energy state for this particular structure, because these guys are happily ganging up on this guy. I know, right? People. So what, right? So yeah, it's not morally good, but it actually gives you an interesting predictive tool. Because if you have a graph and you can start to look for opportunities to close triangles, you can start to mutate the graph. You can start to predict how it's going to look. Anyone believe me? I have a historic proof. You've been dead nice to me. There's something weird going on here. I have historic proof. Hello, Europe. I say that now. I may not be able to say that after the 22nd of June, right? Screw you guys, so the man says. So look, this is old Europe, right? These are the great houses of Europe, kind of 160, 170 years ago. And in this graph, the black relationships represent friends, and the red relationships represent enemies. I mean, yeah, this is classic kind of big geopolitics being played out here. But now that we know the rules about triadic closure, what happens if we start to iterate over this graph? Well, let's see, right? So, okay, we've got this kind of strong triangle here between Austria, Germany, and Russia. For the sake of speed to get through this so we get to the beer, I'm just going to call those the bad guys. Just it's not subjective, it's just a macro, okay? You read into that what you will. Look, all I'm saying is Bond bad guy, can't tell the difference, right? So Bond bad guys, right? just performance enhancing. So anyway, so then here comes Italy, because, you know, nothing really goes wrong when Germany and Italy get together, and they form a lovely, sorry, Lorenzo, they form a lovely, stable triangle here, right? So they're all friends now, right? That's almost certainly nothing bad comes from friendship, right? So, okay, this is all going well. We've got some stable stuff. And then this happens. And so it's like, oh, okay, well, now Austria and Germany are mates, but they really don't like Russia. And that's stable, right? I mean, it sucks, right? Because it's like Austria and Germany, and it can now gang up on Russia. And that seems a bit kind of, you know, unfair. But it's a stable triangle. So just iterating through, of course, graph theory doesn't know about the geopolitics. It just knows that it wants to make triangles. So we carry on going through. Then this happens. So the French and the Russians become friends, and they gang up on the Brits. And you wonder why we're having a referendum, Johnny France. God. Anyway, so then what happens is really weird, right? And the graph doesn't like this, and actually nor do the peoples of France and Britain, for what it's worth. But this is called the Entente Cordiale. And the graph hates this, right? Because, like, France is all like, hey, Russia, the Brits are cool now. And Russia's like, no, hating on the Brits. It's kind of awkward, hashtag awkward back in the day, right? So the graph resists this. And so what does the graph do? It tries to stabilize. So actually we do. The Brits and the Russians become friends. And if you iterate over the rest of this graph, you ultimately get this. This is now a fully closed graph. All of the connections have been made, and they're all stable triadic closures. These triangles are in the low energy state. It's brilliant, right, for graph theory, because graph theory has just predicted the starting point for World War I. I mean, yay, graph theory. I mean, boo, humans, but yay, graph theory, right? So the graph theory, knowing nothing about any of the politics going on here, has correctly predicted the start of World War I, which is amazing, right? I just don't know any other kind of predictive analytics that could do something quite so cool. But of course, that's historical. This is what happens in... I don't quite know how I'm going to science my way out of this one. Anyway, even graph theory can't predict the outcome of this, I tell you. So the lovely thing about graph theory is that it can give you this amazing predictive tool. And it's really simple, right? You're making triangles, closing those, making those closures, you're relieving the tensions in the graph so everything's in a low energy stable state. Amazing, amazing, simple predictive tool. But the lovely thing is there's nothing special here, right? So when you're applying that theory to practice, there's nothing special going on. Right? You're not going to have to build some crazy-ass data warehouse to do this. You can run your graph analytics on the same cluster that you're running your online stuff. In fact, that's really nice, right? Because then the gap between the things you're analyzing and the things that are happening in the business that make you money is super, super close. So you've actually got one graph for all of your queries. It contains all of those dimensions, and you choose at query time which you're going to fold in, which are important to you right now while you're doing those analytics. So that's rather lovely. But then what about very large jobs? Right, so, Neo4j is a database. It's great. I love it. I work on it every day. I also like graphs, I think was the phrase. And what about when I really want to compute something? What about when I've got a static graph to compute over? Well, we can do that, right? We can still do a computationally centric analysis with things like Spark. Now, the Neo4j guys, we love Spark, right? Spark's a lovely bit of kit. What's lovely about something like Spark is that you can spark up a virtuous cycle where you've got the Neo4j database being the repository for your model, for your knowledge, and you can run a compute cycle over that database that continually enriches it. But what's really lovely is that Cypher, Neo4j's query language, has become open Cypher. It's going to be a standard, and that the Spark team, or the Databricks team and Amplab behind Spark, are actually bringing Cypher to Spark. So the same query language that you use to do your storage and compute jobs can be the same query language that storage and query jobs can be the same language that you use to do your compute jobs, which means that you end up with an architecture rather like this, where you've got an app which speaks Cypher to the graph. Whether that graph is a compute graph, a static compute graph, or a dynamic storage and query graph, you've just now simplified greatly your development cost. And in fact, that's fairly unremarkable, but you could even imagine, because science, I would hypothesize that you could even at some point, or we could even at some point, understand the semantics of particular Cypher queries and start to be able to dispatch them to the database or to the compute engine based on their needs, based on their requirements. Whether I can analyze a query on the fly and decide I'm going to dispatch to compute or query, which is kind of exciting, right? Because then you've got this kind of graph platform which supports all of your compute and query needs, which is sort of cool. So, that being said, there is currently an interesting discussion going on in the database space as a whole between this notion of native and non-native. And I think that's well worth investigating because it's quite a technical thing, and I guess you're a relatively technical audience. So my colleague Max DeMasi, who sadly couldn't be here today, he's over in the US, he's a measurer. He likes to measure things. He's always kind of likes to test people's claims, including, by the way, the claims of the Neo4j development team. He definitely keeps our feet to the fire. And Max was enraged about, some bloke on the internet publishing some numbers, and he thought they were ridiculous. So he started to test things. He started to test things in a reasonable way. And what he discovered was that the claims that were being made by some folks on the internet, that guy on the internet, didn't really hold up to scrutiny. And it was an interesting thing that Max observed, that when you're doing graph queries, the nature of your underlying technology made a huge amount of difference. Now, Neo4j is what we call graph native. So that means that from the query language down through the Neo4j APIs into the kernel, and even down to the disks, we're optimized for graph. Right? That's our normal workload, and that's the thing we optimize for. Some other tech is now, starting to see the value of graph. I mean, you guys all see it, I see it. Other folks outside of this room are now starting to see it. And they start to say, well, actually, wouldn't it be nice if I could drop graph capabilities or graph features onto my thing that's optimized for something else? For example, it could be optimized for documents, or it could be optimized for keys and values, or it could be optimized for columns or something. And what Max found was, when he was measuring these things, that when you were doing real graph operations, that the native stuff always outperformed. And I thought that was really interesting, right? And I think it really boiled down to some fundamental computer science. Now, many of you get a chance to talk to the Neo4j engineers today, but ultimately in Neo4j, we have this property called index-free adjacency, which is like kind of computer science gobbledygook. Science, marketing team, tick. And what that means is when you are traversing the Neo4j graph, usually you're paying a very cheap algorithmic cost, algorithmically order 1, to hop through the graph. That's quite a cheap thing to do. And you have relatively few index lookups. In fact, if you were at Martin Edam and Petra Selma's talk, they would have told you that typically in Neo4j, index lookups are used for finding the starting points. But graphs Neo4j is not a very index-heavy structure. We tend to use the much cheaper traversal pattern to find our informational goals rather than go into global indexes. And what that means is algorithmically, most of the time in Neo4j, the dominant feature is an order n times 1, traversal, which is pretty cheap, right, in terms of algorithmic complexity. Whereas if we were faking a graph, if we were non-native for graph, and we had to go to some global index all the time, then our algorithmic complexity would be n log n. I'm really scoring science points right now, by the way. What does this mean? It means if you have something like a graph of a billion, a reasonably modest graph, then you're going to need somewhere in the region of 12 IOs to find a particular item in it. That's awful, right? Considering that could be n times 12 IOs. That's a big lot of work. In Neo4j, it's order n, so it's super, super cheap. So Max kind of prompted me to think of something else that was kind of, oh, thank you, Rafflecopter. Max suggested Max's work suggested to me that if you are convinced by vendor benchmarks, maybe you should measure yourself. So the thing is, in Neo4j, right, we kind of, we're Swedish. Like Swedes, you might have noticed, don't really go around bashing people. So we have our own internal benchmarks, and we watch those, and we always try to improve. But we don't go publishing numbers, because that's just like an awful pissing competition. But other people, third parties, do publish numbers. I know there was a hardware vendor that benchmarked Neo4j against a non-native graph library on top of an optimized for different workload database. And we were about 1,000 times quicker. That's interesting, right? Because it turns out that index-free adjacency, that pointer chasing, that algorithmically order 1 stuff, isn't just some sciencey thing that I used to wind up my marketing team, but it's actually a competitive advantage. We can explore an awfully large graph in Neo4j. Why? Because we know how to do relationships right down at the basic kernel and disk level. We're not pulling stuff out of columns or documents, figuring out in some application layer what to do next, and rinsing and repeating. We're doing extremely efficient things down at the bottom layer. For what it's worth, if you're thinking about production graphs, what that data suggests is that you can either build a cluster of 1,000 machines to do the workload, or you can use my laptop to do the workload. Now, while some of you will find 1,000 machines sexually arousing, I will point out that is the wrong reaction. 1 machine, way easier to manage, or small numbers of machines. Now, such is the life of of telling your CEO about this stuff, but he pinched my material this morning, right? God damn him. So anyway, the EvaJam guys benchmarked Neo, as Emil mentioned this morning. And it's really interesting because these guys have no axe to grind, right? They could pick any tech they want to serve their business needs. So it's like, fine, whatever. But what I thought was interesting about this is a little while ago, I saw some other Volkswagen-style numbers from some people from a non-native graph. And in this case, it was a very, very similar kind of a job that was done. But in Neo4j, it took about, let's see, I actually do have the science here. It was about 30 times faster than the other tech. It was a graph that was 3 times, this is a graph that's 3 times larger. And it took about 1/4 of the hardware to achieve the same goal. And that's the value of graph native. Now, I think graph native or X native is really interesting, right? Because you've got the analysts out there, the kind of industry analysts, and they're saying, particularly Gartner, they're pushing this thing called multi-model, which I think is fascinating and kind of interesting, right? Because you'd like to think, well, can I repurpose my database for things? The problem I think I have with that thinking is that they suggest that all models are equal. And I don't believe that's true anymore. Certainly, these numbers don't suggest so. I think we're entering a period where we've got native for X, non-native for Y. So, for example, in Neo4j land, we are native for graph. We're non-native for document. So something like structure layers a beautiful document-centric layer on top of Neo4j and allows you to explore linked documents. There's an API if you're kind of a fan of the web style of building structures. And I think other databases are learning this the hard way. If you are native for columns and non-native for graph, that you're going to kick ass at columns, but you're not necessarily going to kick ass at graph. The value that we have here with structure is that not only do they give us a nice document layer, which we are non-native for, but they also they get value from those links between documents. So it's actually a very high value thing to do. So I'd like to think that next time you're picking some data tech, have a think about, pause for thought. Yeah, I may have a very challenging business workload that I want to throw at this technology, but what's the thing that it's fundamentally good at? And then what are the things that I can layer on that which are sympathetic to it, and what are the things I can layer on that that are not sympathetic to it? I think it would be a very illustrative question. So, the future. Of course, it could be the past. This is Doctor Who, after all. It could be the present. Probably, I don't know. It's confusing. So this one's for my people. What is going on? If you laughed at this, you are hardcore, and I love you. What's going on in Neo4j Labs? Actually, a lot of good stuff's going on, right? So, you may see us as this, impressive delivery machine that just happens to deliver to every Emil Ephraim keynote another amazing version of Neo4j. It's the swan, right? It's elegant and graceful, and he's like, hey, give me credit. Actually, there's a whole bunch of paddling like crazy going on under the covers, and I'd like to let you into it. It's pretty interesting stuff. So 3.0, which you can now get your hands on, which is great, has a whole bunch of clever stuff going on from our Cypher team. You saw earlier, as I said, Petra from the Cypher team talking about this. But we have a new cost-based optimizer for writes, so writes go quicker. We now allow you to do parallel index creation, bolt our lovely, lovely message pack from Facebook-inspired protocol. Is super fast and super impressive. There's a ton of other usability improvements, like where we've just taken the opportunity to refine features and make them quicker. And you're going to get a whole lot of value from this. You're going to find that Neo4j 3.0 just sings. It's just going to go that bit quicker by magic than your previous versions. This kind of research and development effort is ongoing in Neo. But there are also things that we do that are discrete pieces of R&D. Obviously, we do horticulture. No, of course we don't. So the Technical University of Eindhoven and my colleague, Max, hi Max, and George Fletcher at the University of Eindhoven have been working on things called path indexes. So this lovely thing about graphs, which we really haven't taken full advantage of yet, is they've got shapes in them, right? Keys of values don't have shapes, but yet we persist or have persisted in indexing graphs as if they were just key value thingies. But graphs have far more than that. They have paths through them. They have well-trodden paths. They have shapes. They have triangles, for example, or stars or diamonds, all this kind of stuff. So Max and subsequently some more research that's gone on into this kind of notion of path indexing so that you'll be able to teleport across large sections of the graph. You'll be able to index shapes and paths that are interesting to you. It's the first time I've ever really seen people think about indexing shapes rather than indexing individual lonely items of data. And that's very, very promising. We've also got Petra Selma, who many of you hopefully saw today, and the folks at the University of Birkbeck, who are doing approximate queries. So this is kind of nice for exploring. You heard Ma make her plea for, please tell me other things that are going on. Well, wouldn't it be nice if the query language or the database could tell you similar things that are going on? And so what Petra's done in her research, which will be continued at the University of Birkbeck here in London, is give us the ability to relax the strict description of our paths and start to get kind of fuzzy description of the shapes we're looking for. So now I can have an approximate query. I return the exact matches first, but then I can return a bunch of approximate answers, which might shed more insight. So for example, if I want to know people who are involved in football, obviously as computer people, many of you do, I might want to find not just people who play football, but people who watch football, people who go to the pub where there's football on, that kind of thing. Kind of relax those queries and have the database do that work for me. And then given that, we can also start to do potentially inferencing work. So it's like, yeah, tell me about cats that like football, or mammals that like football, indeed people that like football, and have the database do that kind of exploratory work on our behalf. So this is work that's ongoing. So Petra's at the end of her period of research work on this now, but this is work that's actually going to carry on for another 3 or 4 years at Birkbeck. It's going to yield some really, really interesting and powerful analytical tools that come from this. The database is going to start to do much more of that hard work so that you don't have to. Indeed, not to be outdone, even inside Neo4j, we're starting to do some fascinating research work on mechanical sympathy. Computers have changed. Computers have changed radically, and we haven't noticed. But actually, for since the last 4 or 5 generations of Intel, the source of truth in a computer is the L2 cache, not RAM. I know, right? What does that mean? It means most of the time when we're writing software, we're doing it wrong because we're doing the worst possible thing, which is we're detonating our caches all the time. Your CPUs are sitting there stalling, waiting for data to be fetched to them. The Neo4j team, the kernel team in this instance, have done some brilliant engineering to try to be more mechanically sympathetic with the platform we're running on. Now we have small pointers. We have relative pointers and we have pointer compression, which means we can fit more pointers and therefore do more pointers in cache, therefore do faster traversals. Even things like refining our page cache architecture so that it lines up to powers of 2, so that we don't get full sharing and stuff, means that our underlying kernel is going faster and faster all the time as we learn the science of what the machines are doing, so we can apply graph science to it. And we're also doing some distributed system stuff. This is what my team does, actually. So we really wish the distributed systems were a done deal, right? I mean, we should just be able to download some middleware off the internet, plug stuff together, and boom, finished. But it turns out that distributed systems is still a very active research area. It also turns out that distributed systems for supporting graphs is rather unexplored, and we're having to do it. Now, despite that, there are bold claims out there on the internet that you can have it all. You can have, safety and scale and performance and good looks and charm and all that. And, we kind of find that a little bit. Shame on you for laughing. That's a terrible speaker thing. They show you some minions, and you're all like, oh, it's like a bad technique. But anyway, this is kind of like informally, this is kind of tension. This isn't Kappa or anything. This is just like my feeling about the tension. That you can try to optimize your space within this triangle such that you can be, efficient, safe, but, you're not going to be a zillion scale. And you can try to do scale and efficiency, but you're not going to be all that safe. There's kind of some informal tension going on there. Don't worry, there's no theorem or anything there. I'm not going to try and claim that I'm like, Eric Brewer Mark II, but this just feels qualitatively, there's something at that. You've got to make trade-offs. That doesn't mean that you pick 2 and leave 1. It means that you have varying levels of support for each of these. And your job, or my job as a systems designer, is to kind of maximize the things that I want, to the best of my ability. Now, formally, however, as Fisher, Lynch, and Pattison told us back in the day, there is a trade-off between availability and reliability. That's fundamental, right? That's proven. Now, availability is the property of a system that it can respond to a request even in the event of failure. Reliability is the property of a system to give you the correct answer even in the event of failure. So actually, availability can be relatively simple to solve if you don't care about reliability. You query me, I just give you a random value back. I am available. You send a write to me, I dev null it, I am available. Right? It's pretty straightforward. More databases than I'd like to mention are sadly down this end of the spectrum. Reliability, on the other hand, is the opposite of availability, because if I'm broken in some pathological way, there may be no chance for me to actually compute the correct answer that you need. So I may just... I want to answer you, right, but I just can't. I mean, it's like I can only tell the truth. Right, you want me to tell you you're a handsome audience, I'm going to sit here all night. That's how to make friends and influence people. So there's a real trade-off there, right? Now, funnily enough, in some kinds of databases, aggregate-oriented databases, so columns, documents, and so on, this problem is a little bit simplified because all you need to do is agree on one value, right? So I agree that the value 42 is in the database at a particular location, and then all of the replicas, so kind of replicate that in some way. And there are all sorts of interesting, cleverer and less clever concurrency semantics, like last right wins at the kind of unhelpful end of the spectrum, right the way through to things like vector clocks for reasoning about ordering and causality at the other end of the spectrum. So you can kind of get in a kind of aggregate database, you can usually get the kind of semantics that you want. You can usually get data replicated. Now the problem for graphs is that relationships are two-way. So that is to say, if I say that I know Emil, Emil has to agree in his record, not that he knows me, but that he is known by me. There has to be some kind of symmetry there. Yeah? If I say that I love Emil, he has to know that he's loved by me, rather than reading his email, right? He doesn't have to love me back, but he has to know that he's loved. Now, when you delay, right? It's just, it didn't seem sincere, did it? So this is it. We're going to have words about this heckling, okay? We will talk. You are in trouble. So it needs to be two ways. And actually, that poses like a really difficult challenge for distributed systems, right? Because we need two records, potentially on different machines, in different data centers, in different continents, to agree with one another. And that's hard, right? There's no getting around that. That's hard. Sometimes you need to get agreement between computers, and that is a difficult problem. Let me show you. So here's a graph that I've drawn that happens to be in a non-native, non-graph database. So it's kind of a JSON database that I've invented. And you can see here that I've got this document here that represents the United Kingdom, still with Scotland for the moment. And you can see that node 1 here is country UK, loves 0, direction out. So, okay, who's 0? Oh, this is 0, great. And you can see that he loves 1, direction in. Brilliant. They're consistent, right? So you can see that that implies that loves relationship. It's what we call the special relationship in geopolitical terms. You may see it as an abusive relationship, but that's special. That is special in its own way, right? So we're all happy here. This is a good position to be in, right? This is the one that avoids drone strikes. This is a good relationship overall. I know, right? Yeah. Well, look, right, if they're going to drone strike me, I mean, it's Mark Cabra that's going to get a polonium sandwich. So we're both in trouble. Londoners, yeah. The rest of you are like, what? You guys eat polonium? Is that Marmite? But what happens when the French turn up? Yeah, what happens when the French turn up? What happens if the French are busy, deleting our love for the United States while we're busy emphasizing it at the same time? What happens? Are we still in love? Are we not still in love? Are we targeted? Anyone got an answer? No, actually, we don't have an answer. The point is, it's like we don't know. But, thanks, France, for trying anyway, obviously. Entente cordiale, people. So we don't know. This is a problem because there is no agreement between these two records that should be reciprocal, because there was nothing to transact them. So for graphs, reliability is far, far greater a concern than availability. But actually, reliability does not have to mean slow. The Google folks do very high-performance transactions, and I think we can too. But that is a surprising thing. Oh. It's not my kid, I don't care, right? But it's like, oh. But I've heard of databases that do this without transactions and consensus protocols, so they're amazing, right? No, they fail, right? We know this. The science says so. The science says they will fail, so no. So what are we going to do about it? Well, we're on an interesting journey. So, anyone know this? So it's this brilliant book written by these young, enthusiastic software developers before we wrote graph databases and became old, jaded software developers. So Ian and I and our friend Savas wrote this book about rest in practice, and celebrity selfie. So we wrote this book, and Ian and I have long been kind of web heads, and Savas has now disappeared to the bowels of Facebook, so we don't know what he's doing, and yeah. Oh, hi, Emil, you wrote a book as well, didn't you? Yeah, okay, bugger off. Yeah, heckle me again, CEO. So we've got this really interesting idea. The web's brilliant, right? Paul Downey, the web is brilliant, right? Yeah, there you go, proof. British government says yes. So the web's brilliant, and it scales really well because you've got like web servers and like all kinds of clever stuff in the middle, and then you federate load out through this amazing application protocol called HTTP, and you can do wonderful things like cache content and so on. The web scales brilliantly. It's the only truly web scale system, despite what certain document databases say. Now, we're working on something that's very, very web-inspired. We call it Core Edge because engineers named it, and we're crap at naming, hence Neo4j. But our idea is just like the web, that you have this kind of core group of machines that are safe and authoritative for your data. And then you have many, many edge machines, which are disposable instances. They are still full graph databases. You can send amazingly fantastic queries there and have them satisfied in millisecond scale, but they're disposable. So you can bring up many of them. They're kind of, they're your army of pawns, P-A-W-N, right? Just not sexy. So you can then have this wonderful duality where you've got super safe data in the middle, which is committed transactionally, so it's all nice and safe and durable and all that good stuff, and still have massive scale on the edge. We do this with a protocol called Raft. Raft is a piece of work out of Stanford by Diego Ongaro, and what Raft does, it enables us to simply keep logs tied together. I only realized a few weeks ago that's why it's called Raft, by the way, because it's a bunch of logs tied together. Yeah, I know, right? So what we're able to do is take Neo4j's transaction log, which is the very beating heart of the way that you interact with the database, and tie it together in a way that is tolerant of failures, and in a way that even if there are faults, you can still make forward progress. So it's non-blocking, even in the case of faults. You only need a simple majority for this to work. And why would we want to do this? Why wouldn't we just say good enough is good enough? Because Sweden, right? Am I right? I'm losing Tobias now. He's like, hey, wait a minute, this is one bash too many. Sweden is a byword for boring. Sorry, safety, 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 safety. It's obvious that you do need to drive around in the daytime with your lights on. But actually, all kidding aside, we in Neo4j, we value safety. You're entrusting your data to us. So there is no way we're going to play fast and loose with it, right? We're going to do all the safe things. We're going to do all the airbags everywhere kind of things to keep your data safe. But we also want you to have a great experience. We want you to power massive apps with Neo4j. Right? We want to power massive globally scaled apps with Neo4j. Right now, the biggest Neo4j clusters I know of are just hundreds. But with Core Edge, you could take that quite easily to thousands or more. And you could do it with something like this. So you could deploy Core Edge such that you have a particular DC that you favor. You put your core machines in there, and you scale your edges around the world. And in fact, you can even have edge machines, instead of catching up directly from core, catching up with one another. So you have a log scale out. So you have a tree scale out. You could feed many, many, many more machines this way. Send your reads to the core, do your writes from the edge. Even then, you could architect for global resiliency, so geographic resiliency. You could spread your core machines around your DCs. Effectively, you have a rubber stamp of the same architecture in each data center. So in this case, you've got a number of core machines around. You write to the local data center for you. The Raft thing happens. And what's lovely about this is because Raft only needs a simple majority to work, the slow machines don't impact your performance. You're act and you're off running again, so you don't have to wait for that slow machine in Australia to respond. This is lovely because it means that you get strong consistency of these machines. You get that transactional guarantee that we know is the bedrock of building safe systems. So a note on that, right? We don't play dice. In Core Edge, transactions are always rafted. But at query time, you can actually make some choices about the level of consistency that you choose. Because the edge servers are eventually consistent with respect to core, you can actually do any of these. So you could read from any edge, just arbitrarily. You could read your own writes from edge, so you can make sure that when you're reading from an edge, you won't get a response back until your last write has been propagated there. You can read any from core. Core is usually consistent, so you can read any of those. You can read the leader from core, so leader is a particular role in Raft, which is likely to be the most consistent. Or you could even have linearizable, which is the holy grail of distributed systems. You could read from a core at core. In increasing levels of expense, but increasing levels of consistency. But what's really nice is that read your own writes from edge is super cheap because you've got zillions of edges. It's also super easy to reason about. You write something into the database, any read that you then do is guaranteed to see that write. And we can do that through the same idiomatic driver stack and the same protocol stack that the drivers team have produced. without you having to really worry about it. So all you know is that I write stuff into the database, I pick my consistency level as read your own rights edge, and I know that all of my rights will be present. It really simplifies things, really simplifies reasoning about the database. It's very, very pleasant. So given all that, what do we know? Well, we know it's time for beer, so let me wrap up. We know that graphs are the superpower. Ma had a better cartoon for that, I think, and I feel kind of lame putting Lego dude up there now, but graphs are a superpower, right? Graphs give you insight, graphs give you the ability to crunch data in ways that you just couldn't do a decade ago. We know that Cypher is key to this. Cypher, the spread of Cypher across other graph technologies, other allied graph technologies is happening. Cypher is going to be your primary API to a whole universe of graph tech here on in. And in Neo4j land, we are going to build RAF-powered superclusters. Oh, definitely grown. So all that remains for me to do now is take my biannual yelling from Emil, and to thank you guys for being an absolutely phenomenal bunch of people to spend the day with. It's been amazing. Thank you.